Hello student, welcome back. Today we are going to start our session. It is lecture 5, module 1, Microcontroller and Embedded System. Shongita Roy, Assistant Professor, Electronics and Communication Engineering Department, Narula Institute of Technology. In the previous class we have completed the architecture of microcontroller. Pin diagram of 8051 and also the block diagram. Today's content is 8051 programming model. (8051) programming. It is a high-level programming. It uses a general-purpose programming language using as C. Advantages: easier to learn, faster to program, more portable than assembly language. Now the disadvantages. Code may not be as compact or as fast as assembly language. Good quality compilers are expensive. So this is an example how it is written. In programming C, if you want to add two numbers, the code will be like this: void main, then unsigned char x equal to 5, y is equal to 6, and z equal to x plus y. Same code written for assembly language will be move a hash 0.5h, add a comma hash 0.6h, move r0 comma a. The result will be stored in the register r0. Where the first line move a hash 0.5h indicates a is equal to 0.5 hexadecimal number. Then a with a 0.6 is adding, therefore already a is equal to 0.5 plus 0.6. Now what the result will be stored in the accumulator A, and when move r0 comma a, then accumulator result will be stored in the register r0. Now assembly language development cycle. This is a concept. Rules and syntax. All code is normally typed in uppercase. All comments are typed in lowercase. All comments must be preceded with a semicolon. All symbols and labels must begin with a letter. All labels must be followed by a colon. Label must be the first field in a line of assembler code. At the end of any program must be included end directive. So this is an example how it is written in the console. So main, it is a main program level is a main. Title section, if you give colon, it will looking like a comment, it will not be processed. So whenever colon something you are writing, it will be considered as comment, it will not be processed. You can only view this, no processing activity on this. So org, OH, this is the first line you have to write. Move a hash 10, move r0 hash 5, add a comma r0. That indicates a plus r0. The result will be again stored in a. Jump main. So it will jump to main. Therefore it will repeat again and again. And at the end of this program it will be end. So this is how it is written in the console. It is showing over there. Listing file procedure by the assembler. So these are the machine code and it is the mnemonic. And this is the address from where it is activated. 8051 assembly language. An assembler program is made up of three elements: instruction, assembler directives, instruction used by the assembler to generate an object file. The instructions are not translated to machine code, that is to org end. It is the, by default you have to write this at the beginning and at the end, but these are not directly translated. Assembler controls define the mode of the assembler, that is to produce a listing file. (8051) instruction set. The 8051 instruction set can be divided into 5 subgroups. Data transfer, that is to move instruction used to transfer data, internal and external, to the 8051. Arithmetic, add, subtract, multiply, divide. Logical, and, or, XOR, NOT, and rotate operation. Boolean variable manipulation, operation on bit variables. Program branching, condition and unconditional jump. (8051) instruction set. Mnemonic, source and comment. Mnemonic, under mnemonic there will be destination, source and comment. The level and comment fields are optionals. Means you can write comment or you can write level, but it is not compulsory. The mnemonic is the assembler instruction, that is to move, add. The destination and source fields are optional. It is important to remember that the destination comes first. The 8051 uses 4 addressing modes: immediate addressing, register addressing, direct addressing, register indirect addressing. Immediate addressing. In immediate addressing, the data source is always a number and is specified by a hash. The number specified is copied into destination. Move A, hash 10 moves the number 10 into accumulator. Move R0, hash 01H moves the number 10 into R0. Assembler number representation. Default numbering system is decimal. Hexadecimal number must be followed by a letter H. Therefore, here H is represent the hexadecimal number and must begin with a number, that is to FA. Hex is written as 0FAH. Binary number must be followed by a letter B. Move R0. The following instruction is showing some example. Move R0, hashtag 255. Move R0 hash 0FFH. Then move R0, hash 81B, means the result will be in the binary form and stored in the R0. Register addressing. Internal register A, R0 to R7 and DPTR may be used as the source or the destination. Move A, R0 copies the content of R0 to A. Note, data may not be copied from Rn to Rn, means same register to same register, it cannot be copied. It should be from R0 to R1. Therefore, at destination and source should be different. Direct addressing is used in instruction that affect internal data memory location or the SFRS. The internal data memory addressing range is 0 to 127, that is to 0 to 7FH. Move A, 20H copies the address. Here there is no hash. So it is not the data, it is the address. So move A, 20H copies the content of address 20H into the accumulator. Move 30H, 40H copies the content of address 40H to the address 30H. Move P1, A moves the content of the accumulator to port 1. Indirect addressing. The most powerful addressing mode. A register is used to store the address of the destination or source of data, similar to the use of pointers in high-level languages. The @ symbol is used before the register to specify indirect addressing. SFRs may not be indirectly addressed. Internal data memory may be directly or indirectly addressed. Move R0, #20H. Load R0 with the number 20H. Move @R0, #55H. Moves 55H to the address contained in R0, that is to 20H. Here R0 acts as a pointer to address 20H. Move A, @R0. Copy the content of the address 20H to the accumulator. Therefore, the register value should be treated as address. Only register R0 and R1 may be used for modifying data to or from internal data memory when using indirect addressing. Register R0, R1 and DPTR may be used when indirectly addressing external memory. Addressing mode exercise. What are the contents of register A, R0, R7 and memory location 30H and 31H after the following code runs? Move A, #5. Move R7, #40H. Move R0. Then move R0, 30H. Move 31H. So 1 minute. So move A, #5, that indicates A is equal to 5. Then move R7, #40H, therefore R7 is equal to 40H. Then move R0 is #30H, means R0 is equal to 30H. Then move 31H, #40H, 14H. Then move @R0, A, therefore it will be incremented R0, then move R7, @R0. Therefore, whatever the value of R0, it will be treated as address and it will be moved to R7. How long does the code take to execute if the 8051 is operating off at a 12 MHz crystal? Means its crystal frequency is 12 MHz. Some useful directives. End, last line of code. Assembler will not compile after this line. ORG, origin directive, sets the location counter address for the following instructions. EQU, equation directive, used to equate a name with an address or data value, useful for constant assignments. Data, used to assign a symbol name to an address in the internal data memory. Average data 30H, average, move average, H. BIT, used to assign a symbol name to a bit in bit assemble data memory. Programming sequence. Normal program execution is sequential. The PC is loaded with the address of instruction n+1. while instruction S is being executed. The program branching instructions allow the programmer to alter the program execution sequence. These instructions allow the address contained in the PC to be changed. Program branching is used for jumps, function calls, and interrupt service routines. So this is the program branching instruction. A call, ADDR11, absolute subroutine call. L call, address 16, long subroutine call. RET, return from subroutine. RET1, return from interrupt. AJMP, address 11, absolute jump. L jump, address 16, long jump. S jump, REL, short jump. JMP, iterate A plus DPTR, jump indirect relative to the DPTR. JZ, REL, jump if accumulator is 0. JNZ, REL, jump if accumulator is not 0. CJNE, A, direct, rel. Compare direct byte to accumulator and jump if not equal. CJNE, compare immediate to accumulator and jump if not equal, and corresponding code will be A, hash data, rel. JNE, rn, hash data, rel. Compare immediate to register and jump if not equal. CJNE, iterate ri, hash data, rel. Compare immediate to indirect and jump if not equal. DJNZ, rn, rel. Decrement register and jump if not 0. DJNZ, direct, rel. Decrement direct byte and jump if not 0. NOP, no operation. Jump instruction. The 8051 has two types of jump instruction. Unconditional jump. This instruction type will load the program counter with a new address and will automatically jump to the instruction at that address. Conditional jump. So here the instruction type will only jump if a criteria, certain condition is true, similar to an if statement in C. So it is a test condition. If it is true, it will be jump. If it is false, then to the next instruction. Unconditional jump. The 8051 has three unconditional jumps with a different range. S jump, short jump. A jump, absolute jump. L jump, long jump. For S jump, it is allow a jump of minus 128 to plus 127 byte relative to the current PC value. Instruction is 2 byte long. A jump, absolute jump, allows a jump with the same 2 kilobyte page that the PC is currently located in. Instruction is 2 byte long. L jump, long jump, allows a jump anywhere within the 64 kilobyte program memory range of 8051. If unsure which of the three instructions to use, simply use the JMP instruction and let the assembler decide which instruction to use. Conditional jump. The 8051 can test condition at the bit and byte level. Bit conditional jump instruction. This instruction will jump if a bit is in a certain state, that is to JC level, jump to level if carry bit is set. JNC level 2, jump to level 2 if the carry bit is clear. These instructions are commonly used for arithmetic instruction and for testing of flags. Byte conditional jump instruction. DJNZ, decrement to jump if not 0. CJNE, compare to jump if not equal. DJNZ instruction. Decrement and jump if not 0. DJNZ RN, level. DJNZ direct address and level. DJNZ is used to execute a block of code n times, similar to a code for a while loop in C, very useful for generating delays. Move R0 hash 10, therefore R0 is equal to loop counter. Then loop is equal to DJNZ R0, loop. move a comma r1. Therefore, it will count up to 10 times. When it is fulfilling, then it will go to the next line, that is to move a comma r1. Therefore, whatever be the value of r1, it will be stored to the accumulator. Similarly, for DJNZ, it is move r0 hash 10, then DJNZ r0 loop. Same thing with the earlier, it was DJNZ, it is ten times, moving, it is 10 times. The DJNZ instruction takes 2 machine cycles to execute, that is to 24 clocks. If the 8051 is operating from 12 MHz crystal, the loop execution time is 10 into 24 divided by 12 MHz value is equal to 1220 microsecond. The maximum delay for a single loop occurs when the loop counter is initialized to 0. This will cause 256 loop iterations. Delay 256 into 24 divided by 12 MHz is equal to 512 microsecond. How do we generate delays longer than 512 uses microseconds? So here it is how the delay is created. Move r0 hash 0, therefore 12 clock cycle. Move r1 hash 200, therefore 12 clock cycles. DJNZ r0 comma loop, therefore 256 into 24 clocks. Then DJNZ r1 into loop, therefore execute inner loop plus DJNZ 200 times. Therefore, total execution time is equal to 12 plus 12 plus 200 into 256 into 24 plus 24 divided by 12 MHz. Therefore, 0.102802 second. JNZ exercise. This is an example. Therefore, R0 first line move R0 hash 0. Therefore, R0 equal to 0. R1 is also equal to 0. Then R2 is equal to 10. Then DNZ R0 is equal to loop. Then R1 is equal to loop. R2 is also equal to loop. CJNE instruction. Compare and jump if not equal to 0. So don't worry student, when you will do the program, it will be more clear. There are just example how it is occurring. Now the subroutines. A subroutine is a block of code that can be used many times in the execution of a larger program. Subroutine allow the program to branch to a section of code and to remember where it branched from. When the subroutine is complete, program execution will continue from the line of the code following the subroutine call. Subroutine have the following advantages. Code savings. The same subroutine may be called over and over again. Program structuring. A larger program may be divided into a number of small subroutines. This makes the program easier to maintain and debug. So this is the main program. Call subroutine 1. Then call subroutine 2. This is the subroutine 1, and whenever it is completed, return means from where it has started, it will return to that value. So it is subroutine 2, so it is subroutine 2. So when it is completed, it will come to here and the corresponding, it will be operated. Therefore, subroutine is calling a different program, and from here it is started, it will go back to that position. A subroutine is always executed with a call instruction. When the call instruction is executed, the program counter register contains the address of the next instruction to be executed. The PC is saved onto the stack low byte first. The PC, like microprocessor. The PC is then loaded with the address of the subroutine. The subroutine is then executed. The last line of the subroutine is always return instruction. The return instruction will cause the return address to be popped off the stack and loaded onto the PC. The instruction at the return address is then executed. Subroutine parameter passing. Place the parameter into the address in the internal data memory. Most popular methods used. Push the parameter on the stack. This method is limited by the size of the stack. Place the parameter into the internal data memory. Used when the internal data memory has been used up. Slower execution speed than when using internal data memory. So this is a subroutine how it is calling. So we are not going into detail. This is a structure we are showing in the classes, subsequent classes we will explain. These are the all subroutines. Now the 8051 arithmetic operations. All arithmetic operations are carried out in the ALU. The 8051 has 4 arithmetic flags that is in the PSW register. Program status register. C is the carry flag set if there is a carry out after addition or a borrow after subtraction used for unsigned arithmetic. Auxiliary carry AC set if there is a carry out of a 3-bit during addition or a borrow during subtraction used for BCD arithmetic specially. OV overflow flag if there is a carry from the bit 6 XOR bit 7 used for signed arithmetic. P parity flag. It is same as that of the microprocessor. Contains the parity of the accumulator. 1 if it is odd, 0 if it is even. Useful for serial port operation. Increment decrement instruction. INC source add 1 to the number means if it is r is equal to INC r, therefore r what is the value, it will be incremented plus by 1. DEC, that is decremented, means minus 1. INC A means whatever value of A, it will be incremented by 1. DEC R1, whatever be the earlier value of R1, it will be decremented by minus 1. INC 38H means whatever the value of the previous, it will be decremented by 38H, and so on. No flags are affected by INC and DEC instruction. Multiply and divide instruction, MUL-AB, that indicates it is multiplied. DIV-AB means divide A register by B. So this is an example of addition. Add A comma source, whatever the source, this value, it will be, means the new value of A will be A plus that value. The carry bit C always be tested after an addition to see if the result has a carry of 255. So here 2 bits are added, there is no carry. Here 2 bits are added, there is a carry generated. JC level, jump if carry bit. JNC if there is no carry. So we are not going into detail, it will be subsequent classes, it will be explained in detail. Signed addition, 2-byte number, BCD addition, it will be in the classes, it will be normal classes, it will be explained. It is the general brief idea how the program is done. This is the logical operation AND or XOR, complement, clear, rotate operation RLA, it will be rotate left. Bit level operation, these are the bit level operation. This is Boolean operators, different Boolean operation. CLR for clear carry, CLR for clear direct bit, ACTB set carry, ACTB set direct bit, CPL complement carry, and so on. JB jump if direct bit is set, JBL jump if direct is set and clear the bit. Lookup tables, this is, we will not go in detail here. In the normal class we will continue this. Lookup tables, temperature program, there are some programs. So these are the some of the programming, and this is example. We have already done this one. So we are concluding today's session. This is the references. So thank you. We are concluding the class.